Hey everyone, my name is Ben Prescott and welcome to the YouTube channel for the gradient descent. The gradient descent is a blog I started a while ago. Essentially, I write about anything related to data, more specifically data science and machine learning, but also data engineering and architecture, more specific as it relates to cloud platforms like Microsoft Azure and AWS. This channel I spun off from that blog specific to more in-depth tutorials, some more how-to guides, things that don't really fit well in text format or maybe get a little too lengthy. So the video today that you're about to see is walking you through a project that I did with our capstone team while I was at Northwestern University that revolves around building what's called a convolutional neural network, which is a type of deep learning architecture for a neural network that is well suited for things like image classification tasks. Everything we did was in Azure Machine Learning, and we went through the whole process of how to build and train a model, how to deploy the model, run inference on it post-deployment, as well as how to classify these images that we use, which were chest x-ray images, for identifying the differences between those that may be COVID-19 based pneumonia, influenza based pneumonia, or just our otherwise healthy human lungs. I will put short links to the different time pieces in the description. So if you want to kind of skip ahead, or if you're not interested in certain sections, you can go to that description and find those different areas that you're more interested in. But ultimately, this is more of a kind of a walkthrough of how we did it, the different features in Azure ML, so that if you are using Azure ML or you're interested in using it, you can kind of see how this can be more well-rounded for an entire project. But if you have any questions as you go through this, feel free to post it in the comments. If you can reach out to me directly on LinkedIn if you want, that will be in the description as well. I also plan on posting some additional videos in the future. Again, these are going to be more in-depth tutorial videos. Some of them will be a little bit shorter, but ultimately it's more for hands-on coding, so you can kind of see things in action. So feel free to like and subscribe and follow this channel for more videos, as well as additional posts on thegradient-descent.com. A lot of the data, actually all of the data that we use in the project, is publicly accessible. Everything is sourced from two main repositories. One is Kaggle. So for those of you that are not familiar with Kaggle, you can kind of treat it as like an online data science and machine learning community, if you will, that has things like datasets, discussion boards. People will share their Jupyter notebooks. You can actually run your own notebooks through what's called Kaggle kernels, which is kind of like a hosted compute instance. You can get some of that for free. You can also have a paid tier. It's a great place to go for just overall learning and then accessing a lot of different types of data to play and kind of and learn different machine learning approaches. Another one that we made use of is what's called Mendeley Data. So Mendeley Data is another online repository. This one is very heavy with research data sets. So others that may have collected data through various means may have been used for other different research or just more types of data that would be considered kind of more research or academia focused would be in here. That was just kind of a quick background on the data sets that we used, where we got them from, in the event that you want to go try to reproduce some of this, or if you're looking for places to get your own data, these are two great websites to go. Let's start with the overview of Azure ML. So before we get into the different Azure services, our core tool, I guess, or service that we used as part of this project is Azure Machine Learning. Azure Machine Learning itself is kind of a core end-to-end service to support machine learning initiatives, meaning you can connect various data sets and sources. You can do your training within here on a personal compute instance. You can collaborate on notebooks and version control your notebooks. You can use standard CPU or GPU backed instances specifically for training. So you don't have to do exploratory analysis and training onto the same instance as if you were doing it on your laptop. You can kind of split the instance types so you can beef up your training clusters to support things like neural network training. You can deploy inference endpoints, so you can do managed web API endpoints. You can do standard container endpoints or a Kubernetes cluster, so you can deploy your model. We'll go over that later in this video. And you can also attach different compute instances that are not specific to the Azure ML instance. So for example, if I have virtual machines deployed elsewhere in Azure, I can use those as compute backends for training or whatever the case is. I can also attach Kubernetes clusters that exist elsewhere, container instances, or things like a Databricks instance if I'm using Databricks. So I can use that as all different compute backends. Another benefit to this, and one reason that we used it specifically, was to track different experiments. So you can do this with MLflow and other tools as well. I'll show you and kind of walk you through how easy it is to do in Azure ML, but ultimately it allowed us to do things like various hyperparameter tuning, minute changes to our network architecture, and be able to track that historically, and be able to also visualize some aspects, things like accuracy, training duration. We were able to also record and save every model that came out of those. So I'll walk you through how all that was done. And this will also kind of give you a better idea of, kind of the overall capabilities from a team perspective for developing machine learning and deep learning models in Azure ML. So before we dive into the Azure ML specifics, what I want to walk you through is the different Azure services that we are using as part of this. What you see here is my personal tenant. Everything was ported over from a tenant that we shared during the project. Now, everything that you see here is the exact same as what we did. The only difference is you may see various small changes in accuracy or loss percentages of the models. The real reason for that is the networks are stochastic in nature, so they're not always going to be the same. The results will not always be exactly the same. So you won't see it exactly as it was when we published it, but ultimately everything else is exactly the same. So in this case, you can see a couple different services that exist in my resource group here. You can see things like a container registry, which is used for container endpoint when we go for inference, and I'll walk through that later. A standard Azure storage account. In this case, it is configured for Data Lake Store Gen 2. So we are using a hierarchical namespace. I'll walk you through how we have all that set up. We have a machine learning instance, which is, again, the root of what we're using. A storage account here, a key vault, and application insight that you can all see have the same naming scheme as our machine learning workspace. These are provisioned as part of the machine learning workspace deployment, and these are for things like monitoring, logging. The storage account will save metadata and connection information that comes out of your Azure ML instance. So these are all kind of more specific to the workspace. So if you kind of exclude those for now and just kind of pretend they're part of Azure ML, we're really only using right now 3 different services: Container Registry, Azure Data Lake, and Azure ML. This will change when we deploy a model, and I'll walk through that later, but the only difference there is we're going to actually see a managed endpoint or multiple endpoints deployed that will provide us with the ability to run inference on future data. All right, so let's get started with Azure ML. With Azure ML, the first thing I want to show is that you have a kind of a navigation pane here on the left side. They break this out into 3 core sections. One is author, one is assets, and one is manage. Manage is kind of your underlying infrastructure that will support Azure ML and your different projects on Azure ML. So you can think of this as connecting your compute instances, provisioning compute instances, creating inference instances, connecting data stores or databases or something else that you're going to pull data into the workspace with. You have the assets section, which is kind of for example, if you have like a SQL database as a data store, you may pull in a certain set of tables from that database. That would be considered something like a data set, right? So kind of the slicing that may come out of a full data storage type. You have your experiments, which is kind of tracking what you're doing in the space, your different training runs, being able to track history as far as what you've done. You have pipelines, which kind of provide you the ability to create an end-to-end flow. So being able to pull in data from a source, run all of your different experimentation on it, maybe do some scoring on that, run some inference on it, and also publish your endpoints or your models to an endpoint. And you have your models and your endpoints. So models is kind of an Azure ML built-in repository for model storage. So things like TensorFlow models, pickle files for maybe it's PyTorch or something, some other framework or machine learning framework. You can store your models in here. There is not a specific type specifically that you have to save it as, so you can use many different ML frameworks or deep learning frameworks. Then you have endpoints, which are publishing models to managed endpoints in Azure. So like I said, these could be managed endpoints such as web services. They could be container endpoints as standard Azure container instances or an Azure Kubernetes service instance. In this case too, you can also attach existing ones. So if you have an existing Kubernetes cluster and you want to provision an inference endpoint in that, you can do that as well. And then you have the author section, which is what where a lot of the hands-on work happens. So if you're used to working in Jupyter notebooks, what you'll see in the notebook section is very similar. It's a little different, so we'll kind of walk through it, but very similar for the most part. You have automated ML, which is kind of the Azure ML approach to no code or low code for the most part. So you can kind of create standard training runs for things like linear regression and classification, and you basically select a list of algorithms that you want it to test, and it will kind of do the tuning and best model selection for you. Then you have Designer, which is kind of more graphical flow. So this is a drag drop approach where you can kind of select your data store, you export data from it, you send it to, maybe you run a trigger a notebook, or instead of triggering a notebook, you're actually running individual cleaning and pre-processing steps that are kind of more visual blocks. So this is a way to design an end-to-end pipeline or flow. And you can also use that to save and store your models as well. All right, so let's take a look at data stores. So for data stores, there's a lot in here that we have added, at least in my workspace. The only one that we're going to pay attention to is the one that's labeled Azure Data Lake Storage Generation 2 or Gen 2. If I click on this, you can see a couple different things here. You can see the URL for this. So this is my actual Azure Storage account URL. In this case, I'm pulling in the images folder directly, which is where everything that we store, with the exception of our test data later, is going to be. You can also see the resource group it belongs to, the subscription ID, basically all of the data that surrounds the data storage that you've connected. And now, as I mentioned earlier, right, you can kind of just treat this as the core connection to a storage type. So this would be my core connection to my ADLS instance. You could have one like this for a database or a data warehouse, or another blob storage is not configured as a data lake. You can treat this as just your core root connection. I'm going to flip over to assets. This is a little bit different. So you have data sets under your assets category, and data sets are kind of the individual targets, if you will, that come out of a overall data store. So in this case, I have one, I just named it data lake, and whatever you want. But if we click on this, and this will actually take a minute to load, but you can see I'm pulling in my root directory, which, if you remember from the data store page, is pulling in an images folder. So it's pulling in everything from that image folder and labeling that as an accessible data set to me. And while this loads, this actually takes a minute because of the amount of files in here. I'm going to flip back to Azure. We'll dive into that storage account, go to containers, and here you can see two root folders or two containers that I have. One is images and one is test. Test is not being used right now. Once we get through the inference portion, I'll walk you through why test is used. It's just for essentially some of the scripts that we use will upload images to that folder, and the API endpoint will run inference on those images. I'll show you how we do that later. And here we have our images folder. Now there's a bunch of subfolders in here, and these, since I'm pulling in the root for images into my data set, all of these will be accessible to me in Azure ML. So it's actually what it's doing is scanning all of these, parsing all of these. Now if I go into, let's say field upload, for example, we'll go into an archive folder, train test validation, let's just select train. You can see in here we have normal and pneumonia. So some of these folders, as we brought them in from our data sources, were pre-labeled as what type of images they were already. So in our research, we have COVID pneumonia, we have influenza-based pneumonia, and we have otherwise normal or healthy lungs. Some of these folders, depending on what they came in with, were already labeled. So we can look at pneumonia. You can also see these follow a similar kind of naming scheme. These aren't the same for every data set that we brought in. So we didn't really care too much about the naming standard. But if you click on one of these and click on edit, we can actually get a little screenshot or a snippet of what's in that image. Same if we go through any of these other ones, right? So these are the types of images that we're working with as part of this project. A side note on this that I think is valuable to mention is there's a lot of variation in how these images look, right? You probably saw that just through the two I just showed you. This is a different dimension, more of a landscape style, or kind of more of a horizontal image, whereas the others were vertical. Some have collarbones, shoulder bones, some have a full picture of the lungs, some are cropped, right? So there's a lot of differences here, and some of that's just kind of how various rad techs take images, right? And it's just kind of how the difference in humans are based on how we take pictures or images, in this case, X-ray images. So obviously this is not going to be exactly the same every time. So that's part of the struggle with training a model to identify things like COVID or influenza pneumonia or whatever, is why we need so much data, is because we have so many different variations in the source images that we're using. So let's flip back here. So if we look at our data set now, it's loaded, and we have, you can say it has greater than or equal to 4,000 files. Total size is greater than or equal to 1 gigabyte. We definitely have more than that, significantly more than 1 gig. But anyways, you can see kind of current snapshots. And again, this is pointing in that root directory. If I click on consume, when you create a data set in Azure ML, it gives you the Python code that you can pull into your notebook, and it will connect or load that data set to your Python notebook. So benefit to this is it has things like your subscription ID and all kind of your underlying Azure information already. Here it's pulling in the Azure ML workspace. So the workspace being this kind of instance or tenant or whatever you want to call it that we're in right now. It will pull in the metadata as it relates to what we're operating in at the time. It will look for a data set with the name data lake, which is what this one is, and it will download that to a local path to the machine. Now, what it's not doing in this case is it's not downloading all the files. It's just downloading a link to the data set. And I'll show you how we mount this to a VM when we get to the notebook section. Okay, one other thing we can take a look at is on the Explore tab. This takes a minute to load, which is why it's a cut here. Anyways, you can see some paths, example paths of some files. And you can see file names, the size of the file, and on the right side here, which might not load in this time, but we'll just kind of skip it for now, is it will actually pull in a preview image, similar to what we saw when we were in the blob storage, and we actually looked at one of the images. So you can see some examples of what you have here, so you can also make sure that you're in the right directory, and it's going to pull in the correct information. If there's any models deployed or stored in that data set as well, you can see those models here. All right, so let's jump over to compute instances. So this is kind of where the back-end services exist in Azure ML that support training and inference and everything else that needs to go on within the platform. You cannot operate within Azure ML without any kind of compute instance attached, but that does not mean you can't go back and look at previous experiments, notebooks. Like, you can still view all of the data that's stored because it's all stored in a storage account. You just cannot operate on it. You can't run new commands, new Python commands or whatever it may be unless you have a compute instance attached, similar to anything else. All right, so in this case we can see we have compute instances, compute clusters, inference clusters, and attached compute. Now compute instances, you can treat these as, by standard, they are personal instances to you as a user in Azure ML that you can use to run notebooks, run scripts, do whatever you need to do on the platform that requires compute backend. I can also provision these as an admin for other users. So if I wanted to go in here and provision one for someone else on my team, I could go in and create an instance for them that they can attach to their notebooks. In this case, I just have one for me that's running. One thing that's interesting as part of this project is we are making use of a compute cluster. When we're using a compute cluster, it means I do not need a very strong virtual machine or compute instance to run my notebooks initially, because I'm actually going to offload the training to my compute cluster. So in this case, I just have a very, very basic DS1v2. If I click on this, you can see it's a 1-core, 3.5 gig of RAM. Very basic. The whole purpose here is to keep my core count low and also the cost down. But the whole purpose here is, again, we're using training clusters or compute clusters to do most of the heavy lifting. You can also see by default it provisions various applications for you. So if you're comfortable with Jupyter Lab or Jupyter and you'd rather work with that versus Azure ML's notebooks capability, you can actually launch that through here, and you can see all of your stored notebooks in Azure ML and interact with them through the same interface that you're used to with Jupyter or Jupyter Lab. It does support R as well if you want to use RStudio, or you can also connect this as an external compute source to your VS Code instance too, if you'd rather do development in Visual Studio Code. Okay. Compute clusters, as I mentioned, we're making use of those specifically for submitting training runs. So you can think of, let's say we go through all the pre-processing steps. We have the data ready to, maybe it's split into trained test sets already. We're ready to do something with it. We can have a script that holds in this case, the convolutional network architecture and all of the different hyperparameters and functions that needs to happen as part of training. And that script can be sent to the train cluster, pull my train and test data sets into it, and essentially run my neural network training job. So in this case, this here is sitting at 0 nodes right now. This is only ran or accessible when it's called. So the benefit to training clusters is you can start them out at 0 nodes, where it won't be accruing charges, it won't be running, but when a job is submitted to it, it will start to spin up and provision a node, and that node can then accept incoming training jobs. This can be used by anybody. This is not personal, meaning that anyone on my team can access this cluster and submit their training jobs to it. It can also auto scale. So if you wanted to, say, start at one node, it will turn up and turn up a single node for training. And then if it starts to get overloaded or you submit a very hefty training job to it, it will automatically scale to 2 nodes, 3 nodes, however many nodes you give it and specify. In this case, we have one running, which is an NC6 series. Now this is a GPU-backed series. So in this case, you can see it has an NVIDIA Tesla K80. It also has 6 cores, 56 gig of RAM. Reason for that is we have quite a few images we're sending to it. Convolutional neural networks, actually neural networks in general, can take a long time to train sometimes, especially with a large amount of images. So we're making use of GPUs and using a GPU-based library to do our training. Inference clusters, which we don't have any right now, are model deployment clusters. So let's say you deploy a model to an AKS or a container instance endpoint, you can have those show up in here, or you can create a new cluster, such as an AKS cluster or container in Azure, and attach it in here, and that will deploy your model, the trained model, to it, so that you can run inference or send new data for a result, essentially, to this endpoint. So let's say I train my convolutional neural network, I'm happy with the performance, I package that into a saved model file, I deploy an endpoint and upload or send that model file to it. It's now considered an inference endpoint, so it'll have something like a REST API that I can hit, and I can send a new image to that REST API endpoint. It will do something like all of my pre-processing tests and send it to the network, the trained network, for a result, and it may return something like being COVID pneumonia, influenza pneumonia, or otherwise healthy. I can also add external compute instances and use that as an attached compute. So as I mentioned earlier, this could be standard virtual machines. If you're using Databricks for something, you can also use Databricks as an attached compute here, so very beneficial. But again, these can all be things that you add that are external to Azure ML that would be compute backend. All right, so let's take a look real quick at what's called environments. Environments, we are using one. It's specifically a custom environment that we created. And what this is, if we take a look at it, is essentially just a dependencies file or something that you've specified that it will build a Docker image around. So in this case, you can see our dependencies here. We're pulling in some Azure ML library specifically. TensorFlow. So TensorFlow is our primary machine learning library and deep learning library. So if you're not familiar with that, I would definitely recommend Googling it. And we're also pulling in some additional things that are not available to us out of the box by Azure ML. So like a packaging library, we're pulling in an argument parsing library. These are all things that allow us to pass in like dynamic variables or arguments into the model at training time. So this is where you kind of, you provide dependencies of what packages needs to be installed in that Docker image. And when you go in here, you have this option to build. When you create a new environment the first time, it will automatically run a build. But it will go in here, it will version control this. So you can see I'm on version 4. And here is where it is storing that Docker image. So you can see the repository it's storing it in. At the time you submit a training job, when I walk you through the notebook section, you can see you can actually define this at time of training, or you can pull in a pre-built custom environment or a curated standard environment. So if I go back to the environments page, there's another tab up here called curated. These are provided to you out of the box by Azure ML. So there's a lot in here already. You can see some of these are more geared towards inference, right? So if you submit a model to an endpoint, you can use one of these environments for that endpoint that it will provision off of, because this is kind of geared more towards inference run or inference post kind of training. There's other ones in here for PyTorch. So if you're not using TensorFlow and you prefer PyTorch, or if you're bringing in scikit-learn, you can bring that in as well. And if you click on one of these, you can see specifically where it's pulling it from. So you can see also this is a GPU inference container, or Docker image, I should say. So in this case, if you're using a GPU-backed inference instance, it will make use of the GPU-based environment based on what kind of libraries it's pulling in. Okay, so again, these are more dependencies that you will need. You will need to specify these if you're using training clusters. So anything that is not static, that you are actively installing packages on that save a state, you will need to use an environment for. It's best practice to use one of these anyways, especially if you're submitting elsewhere. I know a lot of people, when they first get started with Azure ML, they'll have this kind of their own personal compute instance, and they'll go in and do like a pip install for all the different libraries they're missing. That's fine for your own personal use, but again, keep that in mind. That's just for you, and that also requires you to be stuck with using your compute instance. So If it's not beefy and it can't handle the training that you need to do, you may need to use a compute cluster or something else. Those will not have those packages. So this is a good way to kind of standardize what you may use and save as a curated or a custom environment. So moving into real quick experiments. So we've talked about storage, we've talked about compute backends, we've talked about custom environments and defining the environment dependencies that you'll need. We also have experiments. So when I submit something, let's say to a training cluster, what it will do first is it will go out and either build a Docker image based on what I specify in my environment file, or it will pull one that I've already created or one that I specify as a curated environment. And it will build that image, start the virtual node, and what it will do is take my submit training job that I'll send to it, and it will tag, in this case, I'm tagging everything into experiments. Now what experiments are is, you can kind of think of it as like training run history, or a way to log what is actively happening in your model training back into the Azure ML workspace itself, so you can go back in time and view history and metrics and anything else that you may log. So for us, for example, we have two primary experiments. We had single layer and multi-layer experiments. So the whole goal here is with convolutional networks, our biggest kind of change or the different things that we varied throughout our training was models that only had one convolutional layer in them, and then we had models that had two convolutional layers in them. And we wanted to see kind of the performance benefits, kind of the training outweigh the difference in training time, all the different metrics, right? And try to identify what's the best model that we can get based on these different metrics and how long it takes to train them, and also the model complexity. So we created an experiment for single and an experiment for multi. So if I click on single, for example, you can see some charts up top, right, that kind of describe things like how many dense layers or fully connected layers my model had when I submitted the training job, how many convolutional filters I told it to use, and then in this current one, the actual training accuracy. You can change these views. If you click on Edit View, you can give it a different name, or if you go in here and click on Add Chart at the top, you can give it a new chart tile. But you can also select what you want to see on the x-axis. A step could be something like an epoch, a training epoch. The y-axis could be something like validation accuracy, right? So you can change these to showcase different things on your initial dashboard for your experiment. You can also see some different stuff here as it relates to each experiment. So when I submit a training run to train my neural network to my training cluster, a part of our code that I'll walk through is we are logging all of those back as an experiment, a unique experiment. So the very first one I ran in a single layer was on the 17th. In this case, again, I just recreated some of this in my tenant so you can see it. But this one took 9 minutes and 10 seconds to run, right? And if I look at this, I just select just this one. You can see this is the training accuracy, which we don't necessarily care about too much here. But if we actually go into create a new one here, we'll select validation accuracy. Here you can see that my peak accuracy was about 65% for that model, right? So the training time was pretty low, but my validation accuracy was pretty low as well. You can also see here we have one that took 1 hour, 15 minutes to run. So if I select that, here's my training accuracy. You can actually see this was around 72, 73% max, looks like. So better accuracy, longer training time. That's not always the case, right? You might actually have a model that trains for a very long time, and it might do things like overfitting, where it actually learns too well with the training data that it performs poorly on something that it hasn't seen before. In other words, it does not generalize well. You may have something that runs for a long time and just consistently gets poor accuracy just because of how the model architecture was set up. Maybe it is overly complex. That is possible, right? So training duration was just one metric we used to try to gauge what was the best model. But ultimately, you can see things like training history, submission time, who on your team submitted it. So in this case, I submitted all of them. But in our project, we could see others like Robin or Juliana or Philip. They could submit training runs in here. You can also see what compute cluster or training cluster that was sent to. So if this is ran locally on my own compute node that I have in here, my personal compute node, you would see that name versus the train cluster name. And you can see what type of run was submitted. In this case, I submitted a Python script, so I'll walk you through how all that was done. If I dive into a run, and we'll just discard this view for now, you can see a couple different things that come in this. You can see some of the metrics that were collected. Now, all of this data that it pulls in, validation accuracy, loss, things like that, I'm submitting back to the experiment itself in the training script. So I'll show you how I was doing that. You can also see arguments that I passed in. So as I mentioned in the environment section, we pulled in argparse, which is a library that allows us to send in dynamic arguments into the model at training time. These are what I passed in. So I told it use 128 filters in the convolutional layer, use only 16 nodes in the fully connected layer towards the end, and give it this name, right? So here you can see it also registered a model with that exact same name. Can see again more information around what environment it used. So version 2 of custom environment is what it's saying here, so that you can kind of go back and see like what dependencies were loaded at the time of training. As I mentioned, you can pull in different metrics at training. So anything that you can collect during your Python script, you can actually send back in here. You can send back standard metrics like I did here. Again, kind of input, number of filters and layers. So the benefit to us is we could go back and say, well, this model got about 73% on the validation data set. How many filters did we use? You know, how many layers was it? In this case, it was a single layer. We used 128 filters. You know, what was the dense node count in the final dense layer? 16, right? So we can kind of see a history of this. The other benefit to this is part of our training script at the end runs the trained model against what's called test data. Test data is the unseen data. So when I get to the section around how we did the pre-processing, test data is seen as, a lot of people call it held out data, where in that case the model has not seen it yet. We run a test against that using our trained model, and we try to gauge the performance of it. What we can do is save those outputs, whether we do it as an image or a metric or something, and actually log those, including images, back to the Azure ML experiment. So part of what we did was we created what's called a confusion matrix, and in this case it's kind of more like a true positive, false positive, true negative, true positive type of scoring image, I guess, if you will, to try to tell you how well it did on this unseen data, right? So in this case, what we want to see more of is darker squares that kind of go from top left to bottom right diagonally, because that means that if it was COVID, it correctly classified it as COVID. If it was healthy, correctly classified as healthy, etc. But a lot of these were misclassified, right? So looking at my second row down, these are my healthy images going across. 214 images were incorrectly classified as COVID that were actually healthy, right? So this is kind of a way for us to gauge performance from the model on unseen data. So again, if you do this as a confusion matrix or a table or a standard metric or graph or something, you could log all of this back to an experiment. So if you're using a training cluster or something, you don't have direct console access to it, or you can't log in to see what you may be used to seeing if you run training through a standard notebook. So in this case, you can actually view the output logs. So here you can see, this is my first epic, my first training epic, right? You can see kind of the validation, or sorry, the training loss and the training accuracy as it goes through the different images that it's testing on. And then we kind of tied off on epic 1, and then it tests that result of that epic against my validation data. So my validation loss, my validation accuracy, right? So you can see what you're used to when you run TensorFlow training on models. You can also see some outputs that I created. So again, here's that confusion matrix. This is part of my outputs folder. You can also see our training script stores the saved model every time it's done training. So you can also see the .h5 file, in this case a TensorFlow file, for the trained model. So we do that as part of every submission, just to make sure that we actually save the model as an output. Another thing that's useful is you can see a snapshot of the training script that was used for that experiment run. So in this case, we used one that was called cnn1.py, Python script. You can see it's actually pulling in all of the core libraries we need. It's doing some initial callbacks. So when we go through the notebook section, I'll show you how this works. And here's where you're used to seeing things like loading your arrays, defining your convolutional architecture. So again, this is a single layer experiment, so you can see there's only one convolutional layer in here. And here we're going through training, doing our predictions on our test data, that unseen data that I mentioned, generating the confusion matrix, and essentially logging all this back into Azure. So the benefit to this is you can say, well, what was the current state of the script at the time of this training? And you can go back and see, maybe somebody forgot to do regularization, somebody maybe did an oops on the architecture or something. It's kind of a way to fact check what was done, just to make sure you're not getting weird results or something that's a little off cuff. So, okay, same thing happens with multi-layer. So I'm not going to spend too much time on this, but multi-layer is exactly the same way. The only difference is if I go back to my outputs folder, snapshot folder, I should say, and look at CNN2.py in this case, you can see that this one's actually using two convolutional layers, two conv2D layers, right? So you can see, again, you get a little bit of a snapshot of what it's using at the time of training. All right, so let's hit on models real quick before we jump into notebooks. So as I mentioned, at the end of every training run, we store a model. We save the trained model regardless of performance. It could be only 20% accurate. It could be worse than taking a guess, right? Does not matter. We save the model. In this case, you can see the different models. You can also see versions. So if you rerun the same training, and let's say you make a fine tune to the architecture, or you had a typo and something failed, or whatever the case is, it will save that same model name just as a new version. So you can actually go in here and deploy that specific version if you want. So it is a version controlled model repository built into Azure ML. You can see the dates it was created. You can see the run ID. So this goes back, if I actually click on this, it will take me back to the experiments training run specific to when it saved that model. If I click on the model, I can see things that it's a custom format. So in this case, I'm custom defining a TensorFlow version, so it's not actually recognizing that, but these are all TensorFlow models. I can view different versions again. So if you have one that you've done multiple times as the same model name, you can go back and see different versions. You can actually see the file output. You can go in here and download that. So if you wanted to download that .h5 file and go load it somewhere else manually, you can do that. You can also see any endpoints you have it provisioned to for inference. So when we go through the deployment aspect of deploying a model, you will see endpoints that model belongs to listed in here as well. All right, we're actually going to skip the endpoints section for now, just because, again, we'll cover that once we get to deploying a model. I'm going to skip designer and automated ML because we're not using those. For us, we did everything code-based. I prefer that personally just because you get a better understanding of what is actually being built into the model, what it's doing. You have a lot more control over kind of the minute aspects of it. So in this case, you can see here, if I actually collapse these, there's 4 folders. So every time someone signs into Azure ML, it will provision a folder for them, a specific user folder. This is storage in that Azure ML, Azure Blob storage that I showed you at the beginning of this video. So these are your own files, your own local storage. You can actually go into others and view their files. So this is where you can go grab maybe like a Python notebook from Robin. You can copy things over, make duplicates, right? So kind of a way to interact with others. You can also restrict this. So if you don't want someone to have admin level rights and view that, you can make sure they don't see other people's folders or files. But in our case, we all had access to everybody else's. Most of everything was moved into my folder at the end just for cleanup. Robin and I did a lot of work in Azure ML, so a lot of what we did was writing in Jupyter notebooks and Python scripts. But ultimately, you can see the file structure. You can also go in here and grab samples. So if you wanted to go in here and create like an AutoML sample, that will actually show you a Python notebook for how to do this. So there's some good examples provided to you if you wanted to do it through a notebook fashion versus through the automated ML or the designer pane. But if we look at our folders, and we'll just click on File Parser, for example, what you'll see if you're used to Jupyter is something very similar, right? You still have your cells, your individual cells that you can run and trigger. You can still add markup or markdown language in here, right? So if you want to go ahead and add text or images or something, or links or something else that goes along that aren't code cells, you can add those in here as well. Something interesting to keep in mind is at the top, you have your compute instance here. So if someone creates a compute instance and shares it with you, you can see multiples in here. But this is the one that, as I mentioned in the compute pane on the left, your own personal instance, this is what it attaches to. It does not attach to a train cluster. So the training cluster that we created is not a compute instance I can use to run this specific notebook, right? This is my personal compute instance. I can also stop the compute instances from here, or I can just go back to the compute pane and click on it and click stop as well. So again, if you don't want to accrue compute charges, you only use it while you need it. Here you also have terminal access, and you can create new compute instances through here as well. Here you can also change your library version. So if you don't want to use Azure ML, Python 3.6, you could switch this to like Python 3.8, use a TensorFlow base, so that'll load in all of the different TensorFlow libraries. Again, this is kind of more, if you think about the curated environments, right? You can use curated environments on your compute instance as well. There's an option up here to edit in VS Code. So this will actually pop open this notebook in VS Code and connect this compute instance to VS Code, such as on like your laptop or a virtual machine somewhere. if you'd prefer to do that. And if you click this little drop down up here in the top left, you have the ability to change what editor you're in. So if you don't like the view of Azure ML's notebook and you want to, again, edit this in Jupyter Lab, you could click on that, and all it's going to do is, well, in this case, it'll tell you that you're going to leave. You may lose some features, the features will change, etc. But essentially, you just click on this. I'll sign back in with my account. And what this is doing is basically redirecting you to your compute instance's Jupyter endpoint, right? So when you provision Jupyter and you spin it up, it's actually a web service, right? So it's doing the same thing here. It's just redirecting you. That's exactly what you're used to with running out of Jupyter. And you can interact with it the same way. As you save changes in here, the changes are saved back into that file that's in your directory. So this will be updated the next time you refresh this page as well. Okay, so let's actually run a couple of these cells. Oops. So what I did here is if I go to view, you have the option to view table of contents. So it's very similar to like if you're using Google Colab or Jupyter Lab, you have the option to see like based on your markdown or your markup language, you can view your table of contents. I went in and just created some for the purpose of this video, so it's a little bit easier to navigate what we're doing. So essentially, the first file we have here is fileparser.ipynb, which is interactive Python notebook. And the purpose of this one is to mount the data lake storage. So that data set that we created earlier, that can be mounted as a local compute instance, or a local storage instance, I should say, to your compute instance. So it's almost like it's a local file folder directory, but it's actually remote, right? So we're going to mount that. We're also going to identify what root folder we want to operate out of. So I'll show you that in a second. We're going to go through and parse every folder and file that exists in that root folder. So the whole goal here is to organize locations and names of what we're going to be using in the future. And then we're going to do some image pre-processing on the data that is found in those folders. Some of the ones that we do primarily are we resize our images, convert images to a NumPy array, and normalize the data. I'll touch on that when we get there. We'll convert the lists, the outputs of those, which are Python lists, into NumPy arrays. And we're going to save those NumPy arrays to our local compute instance. So again, the compute instance this notebook is connected to. And then we are going to take those arrays and upload those back into blob storage, or data lake in this case. Okay, so if you think about what we're doing here, we're just importing libraries, and I'm not going to spend a lot of time on this, but the notebooks are available to you on the GitHub if you want it. We're going to import all the different libraries. I'm going to define a function here that mounts our data lake instance. So as you can see, this snippet of code is well, it's exactly minus maybe a subscription ID, but it's exactly the same thing that I showed you in the Datasets tab, where you click on Consume, and it gives you that Python snippet. You can plug that right in here. Some additional pieces that you can find if you Google the Azure ML Core Dataset and Workspace libraries is you can do dataset.mount and then start that context where essentially we'll mount it and start running that mount so you can have it accessible to your local VM instance. Here I'm going to just kind of print the folders that it finds in that mount. In this case, we're listing the directory of it. And then I'm going to return the context of that mount so that I can use it later. Okay, so very simple here. I'll just kind of run this, and it does take a second. Now there's an unmount command. So best practice for this is if you mount it, do all of your processing, whatever, you should unmount the data lake instance as well. If you don't and you rerun the mount command, it's just essentially just going to create another pointer with a unique ID. So you can see here it's adding everything into the temp folder with some kind of string or ID afterwards. This will change each time you run this mount context command. And we'll just wait for this for a second to run. Essentially what this is going to spit out is all of the folders that it finds in the core directory from this data set. So in this case, it's going to pull in the data lake data set. And if you remember, when I defined that, I told it just to use the root images folder. So it's going to pull everything it finds in that images folder. In this case, you see that fills upload folder, Robins, train test set, et cetera, all of these different ones, which actually relate to the folders that you see here. Okay. Here in this case, I'm just going to say, well, here's my root folder. So just use fills upload as the folder that I want to use later. Okay. So now we basically told it, we mounted it, we selected the root folder to read and write from. In this case, we're going to define two different functions, one to parse the folders. So essentially all we're doing in this case is looking for folders that don't have archive2. There's a reason some of the data in archive2 was incorrect / wrong. So we're just excluding that folder. We could delete it, but we're just going to exclude it for this case. We're doing a glob over top of that. So essentially it's just kind of an operation done on the folders that tells us to do a search down through each folder within those directories. In this case, we're just going to return a list of all of the subfolders and all of the items within the subfolders. In this next function here, we're creating what's called a pandas data frame, which you can kind of treat it as just as a table. It's a little bit more involved than a standard table, but it's a way for us to view and visualize the different folders and also be able to pull the data in for future, or pull the folder directories in for future need. In this case, all we're saying is for everything in that list that was created in the last step, if the word normal exists in that folder directory, add it into the healthy series list. So we're just creating empty lists and appending things, same with COVID, same with pneumonia. So again, all we're doing is organizing here. We're saying anything with COVID, healthy, or pneumonia, put it in its respective list for organizational purposes. And we're going to return a data frame. So if I run this one, here's my folder parser. So if I actually parse this folder, and I'll add a new cell so we can see what this comes out to be. So here you can see all the different folders that it parsed. So you can see it went through fills upload, which is my root folder. It looked for archive because we excluded archive 2. And it found test folders and train folders, each for things like pneumonia, normal lungs, and then a couple for COVID-19 as well. Now we're going to take that and we're going to send it through for a data frame function. And here you can see, if I actually collapse this, might be a little better. You can see that we've created this to have columnar labels, right? So we have healthy for a column, pneumonia for a column, and COVID. Pneumonia is a bad word because COVID and influenza are both pneumonia in this case, but you can treat the pneumonia column as influenza pneumonia, and COVID-19 as COVID-19 based pneumonia. Okay, so you can see that we have more folders for healthy and influenza pneumonia than we do COVID. It does not mean we have more data, but you can also see that we only have train and test data sets for COVID, whereas we don't have validation for COVID. So there's some balancing that we'll have to do later, but ultimately it's just an organizational thing. In this case, I'm not going to run any more of these because I'm running on a very small compute instance to save on some cores, but what I want to walk you through is we're creating some empty lists, Python lists here. And this is where we're doing our kind of high level, very basic pre-processing over every image that is stored in these folders listed here. So all we're saying is for each folder in those columns, for the folder in that column specifically, so like healthy or pneumonia or COVID, if the folder is not none, so what we're doing here is we're excluding these, right? Anything that comes back is none. And if the word normal is in the folder, so again, this is starting with the healthy images, and if train is in the folder, so we're trying to separate our train and test data, train test validation data. If train is in the folder, do a recursive search through that folder, and for every image it finds, we're using a TensorFlow library called load image, where it's going to actually load the image into a variable. We're doing a reforce of a resize here, or not a reforce, we're doing a forcing of a resizing. So this is part of, as I mentioned earlier, some images are more horizontal and vertical. There's different dimensions, some like 1024 by 768, some might be a 50 by 50. So we're forcing all of the images down to be the same size. It's part of normalization. Something to keep in mind when you do that, you may lose data, right? Because you may be compressing images or trying to upscale images that have a lesser pixel count. So you may kind of reduce the quality, but we tried to pick a target size somewhere in the middle that we could reduce everything down to be exactly the same. We're converting each image to an array of values. So if you think of it as you take a standard picture, right? Every picture has different pixels in it. Every pixel has a numeric value to it. It's typically 0 to 255. And in that case, some images that are grayscale only have one layer of pixels that have 0 to 255. If you have a color image, RGB, it has 3 different layers. You can treat it as 3 different matrices. Each matrix has pixel values, again, 0 to 255, right? So all we're doing in this case is we're saying convert the pixel or convert the image to pixel values in a matrix. We're going to divide each pixel value itself by the maximum value, which is 255. And the reason we do this is what we're doing is called normalization. In this case, we're reducing the variance of the values. So the values will still be scaled or still be the same, right? They will be representative of their color. The colors will not shift. But in this case, the value will be rescaled to be between the numbers 0 and 1 versus 0 and 255. Reducing the variance helps neural networks a lot with the training process. There's more to that. I'm not going to touch on it right now, but that's why we're dividing by 255. We're then going to append that array, that image array, again, remember it's numeric now, to a train array list, and we're going to append a label to it. Label meaning, in our case, we're using 0, 1, or 2. 0 basically says that it's a healthy lung, 1 says it's an influenza pneumonia lung, and 2 says it's a COVID-based pneumonia lung. So kind of just real quick, we're using supervised learning here, right? We're saying that we have example images, we know what they are. So this line says, here's our example image, we know what it is, right? So we're appending this to an array and a train label, which will be array as well, with its respective label. Okay, and we're just going to do this for, we're saying if it's train, put it in a train folder. If it's not train, put it in a test folder or a test list, right? So train test split in this case, pneumonia and COVID as well. This is pretty ugly, so don't judge me too much on it. Obviously, we can make this into a function, make it prettier. It doesn't have to be, basically a repeat over and over again, but you get the point. We're going to then convert those lists into NumPy arrays, which is numerical Python. And we're just going to add those new variables. So in this case, it's like healthy test array, healthy test labels, right? So array and labels, array being the numeric values for the pixels, labels just being the 0, 1, or 2. We're doing the same thing for pneumonia and COVID. Then we're going to save those NumPy arrays as files locally to the compute instance. So this is just saving those as NumPy arrays in my current working directory where this Python notebook exists. And then here what we're doing is just uploading each of those NumPy arrays back into Azure Blob Storage, into our data lake. So we define the root here. We say we're creating an empty array list, right? So we're saying for each file in our current working directory, if it ends in .mpy, which is NumPy, append it back to that list. And then for each name in that list, in this case, create a blob client connection into images processed arrays, which is a folder in our data lake that I'll show you in a second. Create a new blob with this name, and then it's going to upload data from the local file into that blob. So the reason this is done this way is sending and writing data to Azure Blob or Azure Data Lake is kind of weird. You have to actually create a staging file first or an empty file and write data from a source file into that. You can't just do like a standard upload. So in this case, this is where we're creating that blob, or in this case, a file, right? We're creating a NumPy file with this name. And then we're going to open the local file and upload data from it to that blob, okay? So it's just kind of a way for us to write back. Now, if we switch over and look at in this case, we're pulling in images processed arrays, so that's the folder. So if I go to, we're in images right now, I'll click on processed, click on arrays. Here's all those MPY or NumPy files that were created and uploaded, right? So you can see there's various sizes. If we look at the ones that just say array, this one's only 120 megabytes for the test array. But if I look at the pneumonia test array, it's 1.2 gigabytes. Initial thought there is if everything was rescaled to 300 by 300, it just means that we have significantly more influenza pneumonia test images than we do COVID pneumonia test images. Okay. So that's kind of our initial pre-processing step. Another is shuffling and joining. So one that's also in here is, I mentioned having more images in some sets than others. You really don't want to deal with imbalanced data if you don't have to. It could throw off the network. There's other ways of handling how to train networks and other machine learning algorithms with imbalanced data sets. In our case, what we did is we just balanced everything back to a somewhat similar size. So if we actually look back real quick at our paper here, click on PDF, we have this listed in the paper where we actually started with 4,152 COVID-19 pneumonia lung images, 4,494 influenza pneumonia lung images, and 10,860 healthy lung images. That's a pretty hefty imbalance, more specifically with the healthy versus COVID and influenza pneumonia. So what we did as part of this is we selected the smallest amount of data we had, which in this case was COVID-19, and we tried to balance everything as best we could to that, right? So in this case, we ended up with 3,374 images of healthy, 3,327 of healthy or of influenza pneumonia lungs, and 3,359 of COVID-19 pneumonia lungs. So you can kind of understand, we tried to balance. This is much better than it was. Obviously, it's not perfect, but this is not substantial enough to really throw off the training. Okay. Anyways, here's another file. I'm going to hit table of contents real quick. So there's 4 main things that happen in this, and just I'm not going to walk you through like I did the other one, but you have your mount ADLS, so you can treat this as it's not all done in the same notebook. We need to remount it, right? So if this was done separately at a different time, we would just rerun this function. In this case, we're changing our root to that processed arrays folder. So again, we went through and did our pre-processing in the last step, saved it. In this case, our new folder that we want to use is that processed arrays folder. So actually, let's run this, go through what this will do. We actually don't have to do a new mount because I'm on the same compute instance. So let's give this just 1 second. Okay, so let's actually run through the book. So let's run our imports here. We're going to redefine our mount script, or our mount function. We really don't have to, but we're going to do it anyways. We're going to remount just so you can see 2 things. One, we'll just get a fresh directory to work out of, which doesn't really matter, but you can also see how the identifier will change. So we'll let this remount here in just a second. Okay, so this remounted, and what you can see here is a new identifier, right? So this is different than the one we had last time. You can see again it pulled in all those folders within the images container itself. This will not appear this time, so we're going to add a new root directory. Okay, now that we have our root folder, what you can see here is we're going to go through and basically parse all of those files off of our Azure Data Lake instance and bring those into a list for us to use and to perform operations on. So you can see all the NumPy files came over here. In this case, you can actually skip this cell, get rid of that one. If the word COVID's in it, we're going to append it to a temporary list for those files into a COVID list, empty list for COVID, empty list for healthy, and an empty list for pneumonia. So here's an example. You can see if I show that list, it's just all of the NumPy arrays that have the word COVID in it, so we know those are COVID-based NumPy arrays and labels. In the same case, we can do one step down here and do the same thing for train. So now we can further take that and say if it's got the word train in it in the COVID list, put it into a train list and a test list, right? So again, kind of separating train test NumPy arrays. In this case, you can also see we can do an mp.load. So mp.load is a NumPy command that allows us to load an array back into memory. In this case, we loaded in the COVID train list. All right, so let's actually start a new cell here, and we can do mp.load. So mp.load allows us to load in a NumPy array back into memory. So we'll just add this to a variable called test, and we can bring in COVID train list. So if we actually look at this list that we generated in the last step, we can actually see this is a list of NumPy files, right? So one is our train array, which is our pixel values. One is our labels. So if we actually bring 0 is the first item in the list, which is our train array. So let's delete that. So we'll actually bring in our train array and load that into memory. It'll take a second because this again is loading into memory. It's a very small compute instance as well, as remember that. So if we look at test, what you'll see here is a list of pixel values, right? Now these are, you notice nothing is larger than 1, right? Everything is a decimal or a float. That's because, again, we normalize those values to be between 0 and 1, right? Instead of 0 and 255. So if I look at just the first item in my test, this is actually my very first image in my array. Okay, so this is actually an entire image. If I do the shape of this, you can see it's 300 pixels by 300 pixels by 3 color channels. So again, RGB, it's a color-based image in this case. We must have something that signifies color that's not grayscale. So you can see it's a 3 by 3 or 300 by 300 image. Even further, I can take a matplotlib command called plt. Well, plt is the library that I imported. plt.imshow, which is image show, and I can view that image, that pixel image, in a visual aspect, right? So again, this is the actual lung image that it converted to those NumPy values or numeric values. So you can see again 300 by 300. I can do the same thing with my second image in my array. Right, so kind of a way to take a look at what kind of actual data you're working with. Okay. One other thing that we can do here is what's called unison shuffle copies. So what unison shuffle, I'm not going to go through this line by line, but high level of unison shuffle is it will shuffle the array list and the label lists in unison. So to make sure that, for example, if the first image in our array is COVID and the first label in the array is COVID, we don't want it to end up with a label for healthy lungs and then have the wrong label attached to the different image data. So it's a way to shuffle large data sets with various labels and arrays and make sure that the label always stays attached to the array, even though it exists in a different list or different array. Okay? So it's making sure it's shuffled in unison. We're going through these shuffles, and then what we're doing is combining everything into train and test arrays and X-test arrays. So, or train test in this case, train test split. So this is a way to say that our train array may have COVID, or will have COVID, healthy, and influenza pneumonia images in it. Same with Y train being our labels. So it's going to have COVID, influenza pneumonia, and healthy labels. Same with a small split out of our tests as well. So we have 4 new arrays off of all the arrays that we imported originally, and we're going to upload those again back into the grouped folder in our data lake instance. Okay. So kind of a high level, that was quite a bit to go through, but that's the bulk of the preprocessing that we went through as far as preparing the data for training. I'll actually close these real quick. In my folder here for final notebooks, there are 2 things that we want to take a look at. One is submit training. Now this is where the root of the preparation to send to our compute cluster starts. So if we actually go through this, I'll reload these. You can see it's going to bring in my Azure ML workspace information, just kind of where it's located in the SDK version it's running. Here are some parameters that we'll pass in. So for example, if I want to submit a new single layer, which is where my name is here, I can tell it to use, let's say, 5 convolutional filters as part of that model. And let's just say 10 dense nodes at the end for a fully connected layer. And what that will actually do is just also give me my model name. So you can see it brought in single layer -5 for convolutional filter count and 10 for dense node count. So this is what it's going to use to track in experiments, Azure ML experiments, as well as the saved model name, the .h5 file. It will treat both based off of this variable. Okay, here we can define an experiment. So you can actually, you don't have to give an existing experiment, you can define a new one. So we could do test experiment if we wanted, or we could add it to single layer or multi-layer. So if we actually do, let's hop back over to experiments real quick. We can see this is single layer EXPS or experiments. So let's add this in here, oops. EXPS, okay. It's going to give that experiment and the experiment type from the Azure ML core library. So these are all things being pulled in from these different Azure ML core libraries up here. Again, we're not going to go through what each one of these does, but just so you know, that's where it's coming from. That will be stored in a variable. We're also going to define our compute cluster target, so train cluster. So if I switch back over to compute, go to compute clusters, you can see it's actually named train cluster. So this is where I want the job to submit to. And here's the environment that I want it to pull, custom env. So again, if I go back to environments, custom environments, this is the name of it, custom env, right? So this is where you're defining everything I talked about earlier. You're defining it into a training script that will be submitted to a cluster. In this case, I'm pulling in custom dependencies as well. So what it will do is it will use that environment, or I can actually define custom Conda or Python dependencies to load in. So as I mentioned earlier, this is where you can define it at training, or you can load it into a custom environment if you want to. So technically this is nullified, right? We could just use env because it's already pre-built and pre-populated, but I'm showing you this just for training sake. We're going to register that environment in our workspace, right? So we're using this later. And here's where we're defining our run configuration. So we're saying the directory for the script that you want to use when you submit to your train cluster is in the scripts folder. This is the name of the Python script to load. And here are some arguments that we're going to pass in at training time. So again, the number of filters, number of dense nodes, and the name of the model, right? Again, that all came from the last cell here. And here's the cluster. So we're using a GPU cluster, so I'm specifying GPU cluster. Just for awareness, that came in from this section, compute target, and compute target came in from just loading the Azure ML Core Compute Library. Okay, so we're just defining that as GPU cluster. You could give it a different name, but GPU cluster.name. So .name will pull in that train cluster name and the environment that we want it to use at time of run. So again, that's our dependency environment. So if we just run this real quick. Okay, now this section here is where the bulk happens. So all we're doing is saying submit that experiment run using this configuration that we just defined. It will reach out to the training cluster, pull the dependencies in, build the Docker image. It will submit that script that I specified in the last step to that training cluster. And what's going to happen here is if I run this, it's going to actually have a running or a trailing cell output here. So you can see everything that's happening in that training job being streamed back into this Jupyter cell here, or this Python notebook cell. Now, alternatively, you can click on one of these links. It will just bring you to the page on the training cluster where you can see things like the epics, the performance output, similar to like what you would see if you run a training job on your local compute node. I'm going to delete these empty cells real quick. The last one here is run.register model. So in this case, we're going to run this just so that when this previous cell is completed, it will also make sure that it registers it. So you can see it's going to register the model with the model name that we gave earlier. It's going to look for the outputs folder. So this is what the training cluster will save the model to. So at the end of our training job, it will save it into the outputs folder with the model name .h5. Okay, so that's the TensorFlow model extension that we're using. We can define our framework here as a TensorFlow framework. So again, that's what the model type is, and the TensorFlow version that was used to train it. This version can obviously change. In this case, we're just hard coding it. Okay. So we'll wait for this to run, but what this is doing is it's submitting that training job to the compute cluster. So if I switch back over to compute, click on compute clusters, you can actually see in here under runs that I have down here at the bottom some uniquely generated name, Salmon River, that is in preparing status, right? So this is the one I just submitted today that is being submitted to this cluster. Now what this is going to do after a few minutes here is it's going to actually create an idle node or provision a node for us. So you can see it's currently at 0. There are none. It does take a second, but what you will actually see this do is go into from succeeded state to resizing state. And what that means is that it has received the information, received the configuration, it's provisioning a new node, and that node will be responsible for running that training job. Where we're at right now is the train cluster is in resizing status. And what that means is it's actually provisioning a new node, moving up from 0 to 1, right? So you can see it's currently resizing. You can see there is one active run that's sitting in queued status. And now what the run is waiting for is the compute instance to be ready. The reason that took so long and why it's just now doing that is on the environments tab. Remember when I actually submitted a new dependency file to it with the custom environment name. So this used to be at version 4, but it created a version 5 today. And what it actually went through is it did a Docker build here, and it pulled in all of the information, all the different dependencies that I gave it, basically created a new image, new Docker image, and uploaded it to that image repository in Azure, container repository. So that's why it took so long. It went through the whole rebuild process and created a new image. Now that image is available, the compute cluster is going to resize it's going to be using that Docker image that was specified. Okay. So we'll give this just 1 second here, and then I'll flip back over. Okay, so you can see this actually didn't take too long. I just stopped it anyways, just so that we could try to save a little bit of time. It's already gonna be a long video. So anyways, you can see that one node was succeeded. So we have one active run, one node is in busy status now. So if I click on this, you can see it is actively running with one node. If I click on my run, I can see it's still in queued state. So this will actually change in a second once we refresh a little bit. But you can see it's actually generating in the outputs tab some logs, both from the Azure ML side. So you can see again that build log that it used when it created that environment. And you can see some system logs that it's starting to create. So if I refresh this, you'll actually be able to see new logs come in over time. But let's wait for this to get out of queued state. So it still recognizes that cluster is resizing, so it must not have refreshed yet. So we'll give this just 1 second. Now we can actually see this is in running status. So what we'll actually be able to see initially, go to the output logs directory here. You can see some of the Azure logs from when it was doing the image build, right? The whole Docker image. You can see some system logs, but ultimately what we see now is user logs. And in here is our output log. So if we refresh this, we can see it's starting to pull in some of the libraries. So it's recognizing that it's trying to pull in the CUDA library or CUDA framework for the GPUs. So if we look at the standard output logs here, what we're seeing is what you might see if you're used to training networks on a local machine, right? So if you don't have your verbosity changed, you can see things like the different epochs. So you can see here as the epoch progresses, you can see your training loss, training accuracy, and here your validation loss and validation accuracy, right? So again, you can kind of view it as it goes through here. This has streaming on, so as it starts the next epoch, it will go through the same thing, and you can see the performance of the model training as it goes. You can also view your snapshot. So remember, as I mentioned earlier, it will take a snapshot of that scripts folder at the time of the experiment, the run of the experiment. So in this case, remember we use CNN1.py, which is our single layer model. So in this case, if we look at the code here, you can see things like the current state of the single layer architecture for the convolutional network. You can see what arrays we use to load into it. You can see the number of, at least the model function that we used, right? So you can also see things like our early stopping callback that we used in here, okay? So we'll go through the script here in just a second, but essentially you can see all the different training pieces that are happening as it's going through the process. Now, part of the things that I'll show you in the script that it's using is how to log metrics back. So at the end of every epoch, it's logging various metrics: validation accuracy, training loss, validation loss, filter count, dense node count, all of those different data that we cared about during our experiment. We're logging that back into the Azure ML experiment that is running on. So you can see here we went through one epoch so far, so it just kind of has these recorded this way. As it goes through and finishes the second epoch, let's see where that's at. So it actually hasn't started epoch 2 yet, so once it starts that, it will log that under metrics as well. And what it'll actually do is start to show different graphs or charts. So you'll see like line charts kind of displaying the epoch on the x-axis and then the accuracy on the y-axis. All right, so if we head back over to the notebook section, keep in mind that again, I'm using submit training, this Python notebook, to submit it to the compute cluster, the train cluster. But remember I mentioned up here that I'm using the scripts directory. So if I go in here and look at scripts, I can see the different Python scripts. Obviously I just labeled one old, I don't use that, but we have CNN1.py and CNN2.py. The only real difference between the two is one for single layer, one for multi-layer. Anyways, you can see this is where the majority of the libraries are coming in, right? So in the submission notebook, we're not loading TensorFlow libraries or scikit-learn libraries or anything like that. We're doing that within the Python script that's being sent to the compute cluster. So the compute cluster has to have these libraries, which is again why we use that dependency, environment dependency build or image, I should say. So let's go through this real quick, very high level, just to show you what's happening during training. Okay, so again, we're loading just standard Python libraries. We're also bringing in that argument parsing library, which we're using. Now this is kind of the custom callback. So if you're not familiar with TensorFlow callbacks, it's something that the training process can do at the end of every epoch. It can be a monitor, it can be an action, it can be something that it will send back to the initial submission of the training job to perform some kind of action. In this case, we're creating a custom callback, and what that custom callback is doing is sending the logs after the epoch is done. So again, validation accuracy, validation loss, training accuracy, training loss, all that different information. At the end of every training epoch, it will submit that back to the Azure ML workspace. Okay, so this is using some Azure ML commands that came in through, for example, through this. So we have like our Azure ML core run library or command. So we're bringing that in. Here we're also parsing the parameters. So you remember when I submitted the training job, one of the cells asked for things like dense node count, filter node count, things like that. This is where it's pulling that in. So it's adding the argument, it's bringing in the filter count, which is an integer type, or the number of convolutional filters is kind of like a little helper. the dense node count, another integer, and the model name, which is a string. So it's bringing all those arguments into the training cluster from my compute instance where I submitted it from. It's going to parse those arguments, and then I can call args dot whatever the filter argument name is, and retrieve that value. So in this case, args dot filters will be filters, and args dot dense nodes, number of dense nodes. And you can see I'm using that run command dot get context dot log. So it's going to get the context of the current experiment it's running in and log that value back into the experiment. So this is how I'm submitting data from the training cluster back into my Azure ML instance. Here's the command that runs the dataset mount. So same as when I was going through pre-processing steps and everything else, I still have to mount the data lake to my training cluster. And the reason is that's how it pulls in all these different NumPy files and uses those as data for the training run. Okay, so I'm doing this context mount again. Here I'm saying use my train test set balanced folder in the data lake, load in my train, my X train, X test, my Y train, Y test, which again, X values are the numerical arrays or matrices, or matrices I should say, of the images. The Y values are the labels, the 0, 1s, and 2s. Here we're just returning those arrays so we can use those. Here we're defining our convolutional network architecture. So this is the bulk of the neural network component, right, where we're saying, here's our callback. So we're just calling that custom callback we created into a variable named log callback. We're creating a sequential model. So in this case, it's going to run from top down. So everything you see in order is the order that the network is going to run. The first one is going to be a convolutional layer where we're actually providing an input. We could also do an input layer alternatively versus just adding an input to the convolutional layer, whatever, standard stuff. But in this case, you can see we're hard coding. In this CNN2.py file, we're actually hard coding the number of filters. In this case, if we wanted to change this to be dynamic and pull from our arguments that I showed earlier, this would be args.filters, right? And what this would do is pull in that variable or that number that we sent it initially. This is only relevant just because I was doing some testing, so I just hard coded it for testing purposes. Here's a what we call a stride. So in this case, it's looking for 3 pixels wide by 3 pixels tall. So this video, again, is not to go into how convolutional networks work, but ultimately it's going to shift over an area of 3 by 3 pixels every time that it convolves. Okay, so again, that's just where that's being defined. That's hard-coded. You could add that as an argument if you really wanted to as well. We're defining our input shape. So remember, xtrain.shape is bringing in the dimensions of the images. So in that case, remember, like 300 by 300 by number of color channels, right? So that's where it's pulling in that information to define what the initial architecture of the model needs to look like. Now, you can see that output if you print that as part of your training script, or also in our research paper, you can see that here. So when we call the input shape xtrain.shape, if you print a model summary, like if you wanted to see how the model architecture looks prior to training, you will see something almost exactly like this, where you can see again 300 by 300 by 3. Okay, so that's 300 pixels by 300 pixels by 3 color channels. Okay, and you can see the differences in what happens to the different dimensions as it goes through. Now again, if you want more info on how a convolutional neural network works, you can Google that. There's a lot of great information out there. Kind of what happens at a high level is every time you create a what's called a feature map, it uses one of those filters. So remember, we define number of filters to use. It uses a filter, which you can think of the input image as a matrix of numbers. The filter is also a matrix of numbers that is smaller. So in the case of what we define in our network, our filter size is 3 by 3. Okay, so it's a 3 by 3 matrix of numeric values. And what it does is essentially a multiplication and summation from your input matrix, which is 300 by 300, against the 3 by 3. So it's actually going to reduce your what's called a feature map, which is an output of those that represents the original image. So the feature map itself will actually be a different size. So that's actually why you see these 300 by 300 images reduce in size over time to like 149 by 149, but you can also see the number of channels or feature maps it's creating go up, right? So you will see something like this in your summary if you printed it. And then the dense nodes, where you see dense down here, that's when we actually brought in this argument for dense nodes that we defined when we submitted our training job, which you will see in here. In this case, for what we used in our final model in the paper, we used 64. I think we used 10 when we submitted the training job. But ultimately, it's going to flatten a multi-dimensional matrix. In this case, 149 by 149 by 512 of those. It's going to flatten those into a single array or vector, which is massive in this case. So it's 11,366,912 vectors, or numbers, I should say. So in this case, it's flattening it down to a single layer, which allows us to perform a fully connected activation function against it, which will give us a prediction of one of three values, which is what this activation function does. It's either going to be 0, 1, or 2, right? Okay, so the last thing that we're doing here is, this is where we're doing our actual training. So in the last section, we defined the architecture. In this case, we're defining the actual training process. So we're bringing in our X-train and Y-train values. Again, that's our train data, the actual arrays, and their labels. We've defined how many epochs we want to bring in. So we can train it for some number of epochs, whether it be 50, 10, 1,000, whatever we want. We can define how many iterations to train on. We can also define a validation split. So validation split meaning what percentage of our training data we want it to hold off, so that after every epoch, that's what it tests against. So that's how it comes up with our validation loss and validation accuracy metrics. So let's say, for example, we hold off 30% of 100 images, then we're only using 30 images, simple math stuff, 30 images for our split. So at the end of each epoch, it will train on those, or test on those 30 images and try to identify how well it may perform on unseen data that it's not training with. That information is then fed back into the neural network to adjust the parameters internally to try to achieve a higher score or higher accuracy next time. Here's where we define callbacks. So we have two callbacks that we're using. One is called early stopping. Now, early stopping allows us to set some arbitrary number of epochs. So let's say that we choose 100. What it'll do is it'll monitor the validation accuracy metric specifically, and it'll say if it does not improve over 3 epochs, just stop the training process. Okay. So it's a way for us to say, well, let's just set a high number of epochs and use some kind of monitor essentially to identify if we need to stop the training process. Benefit to this is it also helps with potentially overfitting. So if we train for all 100 epochs, it may learn against the training data too well to where it actually performs very poorly on unseen test data. In this case, we don't want it to continue training and getting too familiar with the training data to where it doesn't know anything better than that. So we're doing early stopping on this using validation accuracy. Also, we're bringing in that log callback for the Azure logs. So remember, we specified this in our architecture here. We're just bringing that in so that after the end of every epoch, it checks these callbacks. So one, it will check for the validation accuracy change, and two, it will log the metrics at the end of the epoch back to Azure. And then the shuffle command basically just shuffles the training data at every epoch just to make sure it's not in the same order. Here we're also doing model save. So this is where at the end of the training run, we are saving the model regardless. That will save it to the local training cluster directory temporarily. Here we will be running some predictions. So remember, we have our tests or our train data, which we're using to train the model. We have our validation data, which is that percentage split off of the training data. And then we have our test data, which is withheld, right? It's not included at all in the training process. And that's essentially treated as brand new data as if it were existing in the real world. In this case, for each image, we're doing a prediction against that. So we're actually using our model.predict. We're going to predict the Y value, which again is 0, 1, or 2, for that image, okay? And that's where we're actually generating that visual confusion matrix that we store in our images folder in the experiment run at the end of every run, or the experiment at the end of every run, okay? So we created our plot here, and you can see we're doing run.getContext again, but instead of .log, we're doing .log image, which allows us to save an image back to the Azure experiment. We're just going to name a confusion matrix, and we're returning the output of our matplotlib plot, which is that visual image. And just here's where we just run all those functions. So this is where we define epoch count and percentage split. So in this case, it's 20% split, meaning that if we had 100 images, only 20 of those would be held back for validation. Okay. So that's the gist of what it's doing. Again, now this is not a deep dive into any of this. Like, there's a lot of things I kind of glazed over, but this is the core training aspect that you're probably used to doing locally or in Google Colab or somewhere else. In this case, it's just a script that is submitted to our training cluster at the time of need. Okay, so if we switch back to our cluster here, we can still see one is running. So if we go back into our run, still in running status, let's take a look at the outputs. Where are we? So we're on Epic 6 right now. So you can actually see training accuracy is up to 97%, and our validation accuracy is up to 92%, right? So essentially what that's telling us is that on that 20% that we withheld, those images that are not being trained on, it's returning an accuracy of around 92% for the predicting the 0, 1, or 2 or the Y values. Okay, and you can also see different metrics now being logged, right? So as this improves, you can see validation accuracy. Some of these charts aren't shown because they're down here. So here's training loss and training accuracy. And obviously you can filter by these as well if you just want to see things like your validation accuracy, validation lost, or here's like our filter count and dense layers, right? So again, we're logging all this back into experiments. It's for historical purposes. It's easy for us to go back and not have to retrain anything. And we can also go back and gauge different things like training time, accuracy. We can gauge things like precision and recall based off of the confusion matrix that it will log into images. And we can also generate what's called an F1 score, which is one of the key metrics we use to identify the best model. Okay, so the last section we're going to touch on is what we do with the model once we train it. Okay, so in this case, what I'm actually going to do is I'm going to go shut down my personal compute instance, and the reason is that I'm actually tapping out on cores in the environment that I'm in, because I did not increase the amount of cores prior to doing this video, which, whatever. Anyways, I'm stopping this just to free up the 1 core it's using. But if I go back into models, so at the end of every training run, actually I need to get rid of this. At the end of every training run, remember that we're doing a model save, right? And that model is being sent back into the experiment as an output, and it's also being saved into the Azure ML models repository that you see here. So when our current training run is finished, which will take a while, so I'm not going to pause the video for the whole thing, but these are past runs that were done that will be treated exactly the same. You can see the run ID attached to those. So for example, this first one here, you can see the same thing that you would see with the other run that's currently active. You can see all of the loss and accuracy metrics, right? You can see the confusion matrix that it created, that it outputted, right? You can see the output log, so the historic training epics that it went through, right? You can see all of that same detail for each model. You can also click on a model and you can download it if you want to deploy it somewhere else, or import it so you can see like some of the weights or some of the different parameters internally that it tuned to get to where it's at. You can download it and import it somewhere else. You can also deploy it through here. So what we're going to do is deploy what's called a real-time endpoint. So the difference here is real-time is when I submit, in this case, when I submit an image to it, it will return a result, right? If I submit another image, it will return a result. Batch endpoints are, you might have an intermediary somewhere or a server somewhere that's collecting data, and then we'll send that data maybe nightly for inference to this endpoint and return results, or maybe compute results back into like a spreadsheet or something. This is a way to do bulk loads at one time, whereas real time is I'm trying to simulate it as if it's a running service that maybe like a radiologist or somebody may use as a second opinion. They can maybe click drag into a folder or to a website or do like an upload, like an upload or submission or something like that. It would send a result and return it back. Okay. So if we do deploy to real-time endpoint, we can create a new one in here. We'll just call it COVID Inference, for example. You can name it whatever you want to name it. Here you can select if you're going to do managed or Kubernetes. So for Kubernetes, you have to provision or pre-provision a Kubernetes cluster. You do not provision it through Azure ML. So if you want to do this, you would go into Azure, build a brand new Kubernetes cluster, and configure everything the way that you want, the type of networking setup that you want, all of that. And then you would select that in here as being your endpoint. When you do that, it will actually deploy a new pod for you, and it will have the ML model and everything deployed to it as if it were a container endpoint. In our case, we're going to do managed, mostly because we don't want to deploy a Kubernetes endpoint yet in this case, and we don't have one. So in that case, we're not going to go through the whole provisioning process. And you can add tags, key value tags here as well if you want to. I already selected a model because I went into the model and hit deploy. If you just went to deploy a new endpoint by itself, you would have your list of models to choose from along with their version. In this case, we're just going to use this model that was trained. You can see it's a TensorFlow framework model, so you can also see the frameworks used. Here's where you can select a deployment name. So a lot of times what people will do with this is a blue-green. So they may have one deployment slot for blue, one deployment slot for green. When we go through the next steps, you'll see you can actually balance the traffic between these different endpoints or deployments. You can have scoring timeouts of how long it's going to take to return a result before it errors, right? And then if you want to add this to an App Insight instance for logging, you can do that as well. So for us, let's call this primary. It doesn't really matter. Now, two things that this kind of requires. One is what's called a scoring file, and one that's the dependencies, or a way for you to either upload a dependency file that it will use to create an image, or you select from an existing environment. Same as like when you did a training run with the training cluster. So what I actually want to show you real quick is this scoring file. And let me open this VS Code real quick. Okay, these are all commented out, so just ignore these. This is all kind of a test, but this here is called score.py. You can name it whatever you want. For the case of Azure ML, I think managed endpoints require to be named score. Either way, we just do it just because that's what documentation tells us and it works well. Score.py is essentially the file that it will use to run inference. So let's say, for example, I have an API endpoint that's a REST API endpoint. Let's say I send a JSON payload to it that is an image in JSON format. This tells the endpoint what to do with it, essentially, right? So in this case, we have two different things. We have one part that's loading the model. So the scoring file actually has to look for the file that it will use. This is what tells it what model to use in the inference. So if you have a different model, you might change this name, or you might make this dynamic as a parameter or something. But it's looking for the Azure ML model directory, which is an environment variable that's default to every endpoint. And it's looking for this file, which is the one that will be uploaded to that endpoint when we submit this, or when we create this endpoint. And essentially here all it's doing is it's going to take in a request. So as I mentioned, if we send a JSON, which is what we're going to be doing, we serialize some JSON data, send it to this endpoint. It's going to pull in that request. It's going to look for an image key in there, right, to be able to obtain the value. So we're going to send image with the actual image name, such as like a PNG or a JPEG. Here it's going to look for that image in blob storage. So this is optional. You don't have to do this. What we're doing, and I'll show you the other side of this, is once the endpoint is deployed, the submission form will actually take an image from a local machine, upload it to this blob storage URL, and this scoring file references that blob URL and that file name to make sure it exists, so that we can also save the file for historic reasons in blob. So anyways, it's looking for that image in this URL here. We're going to pull in the get file command from the TensorFlow Keras library, where essentially it's going to load the image from this origin URL. So it's going to load the image into memory into the local inference machine. Here it's going to do the same thing, and you can see this is kind of following the pre-processing, right? So this scoring file is for new images. A radiologist takes a new image, let's say it's very high resolution or something. This is going to pre-process that just like we pre-processed our training and testing data. So it's going to resize it to 300, it's going to convert it to an array, it's going to divide the pixel values by 255, same process we followed. In this case, it has to expand the dimensions of the image. Okay, so this is just something you'll have to do prior to predicting or running prediction on that. So it's going to expand the dimensions of the image along axis 0, which is your column or your rows, and then it's going to run prediction on that image and return the largest value, right? So if we run prediction, remember that it's going to predict one of three values, 0, 1, or 2. In that case, it may return something like 0 is 0.7, 1 might be 0.2, and then 2 might be like 0.1, right? So in that case, that'd be 70%, 20%, 10%, so that's 7, 8, 9, 100, so that adds up to 100%. In this case, all it's going to return for value is which one of those labels had the largest value, okay? So if, for example, our prediction returns 70% being COVID, right, and 20% being healthy, and then 10% being influenza pneumonia, for example, it's only going to return that it was COVID. Okay, we could return probabilities instead of just an overall value, but in this case, we're just going to return the overall value. Okay, so that's what a scoring file does. So we actually have to provide that scoring file into our endpoint when we provision it. Now you can add a dependencies file, like if you have a YAML file or something you want to submit here, you could do that. Alternatively, you could add an existing environment. So remember, we have a custom environment we created. We're just going to use the same thing. It has all the dependencies we would need for inference as well. Here you define the instance size that will be running behind this to take in the data and run inference. Now remember, we're not doing training anymore. The model's already been trained. We're just submitting in and running new predictions against it. So we can actually minimize this. Maybe we'll do, let's see. Let's put this down to 1. So we'll do 1 instance of a DS2v2, which is a 247 gig of RAM. We probably don't even really need that, to be honest, for this, but we'll just use 1 instance for now. Now here's where, if you have more than 1 deployment slot, you can change the traffic allocation. So you can have 0% go to primary and maybe 100% go to a secondary, or like a 50-50 or a 70-30, whatever traffic percentage split you want to do. In our case, we only have 1 slot, first slot, so we're going to take all traffic coming to this endpoint and hit create. And what we'll do is we'll check back here in just a second when this endpoint is created. Okay, so let's finish off on the endpoint piece. So the endpoint was successfully deployed. Obviously, we submitted that scoring file. We told it what environment to use, and what it returns here is you can see our current deployment, which is primary. You can see 100% of traffic is going to that. You can also see it provides us with a scoring endpoint. So this is our inference endpoint. So as we send something or some kind of new data to it, we would hit that score /score endpoint. You can see this size. So let's say, for example, you're doing a blue-green deployment, or you want to do like a primary, secondary, tertiary type of deployment slot. You could go in here, click Add Deployment, go through the whole process again. You could actually deploy different models if you want. You can also give it different scoring files. So if you wanted to do something different per model, a different environment that it needs, you can define that per slot, right, or per deployment type. So this is not just one model. You could have one endpoint that it serves multiple models, and the allocation of traffic is different per model or per endpoint. You can go through here, we'll hit test in just a second, but you can also see consume. Same thing with other things in Azure ML. You get kind of the snippet of code. The core pieces that come out of this are this section, actually this whole section here, as far as like if you want to submit JSON data to this endpoint, or in this case you will submit JSON data. Also how you return the request or the response from the request. So this is good information if you're not used to working with REST APIs or REST endpoints. There's also a primary key here that you'll need for this. So it's also mentioned in the code, but if you're using this or creating your own code, you need to grab this endpoint, which again is that score URL and the primary or secondary key. You can run test data. So depending on how you want to submit, if you want to submit a JSON payload that has an array of values again to kind of simulate an image, you could submit that here to kind of see what result you get. Or also you could submit it through, if you have like, in our case, what we did is we submitted files to the data lake into a test folder. You could call that file in the test. So for example, we'll walk through how to use that real quick. So in my cap images data lake instance and containers, I have 2 containers, one for images, which is what everything was stored in for the NumPy arrays, and one for test, which is where files will be uploaded. And kind of walk you through how this works. I will pull up Visual Studio Code again, and I'll show you. So what we did is we wrote a Flask app, which is a Python library for a web server, and it essentially allows us to spin up a front end, a very basic front end that we can develop in HTML, where we can submit a PNG or a JPEG file or something, and it will save that in the test container in our data lake instance, and it will also submit that file to the scoring endpoint for inference. So if we look at this main.py file, essentially it's a Flask app that's using an upload.html file, which is, let me open this real quick in. This is all it is. very basic HTML file, nothing crazy. It's just running on a local host, right? So that's what Flask is going to run on. It's going to take a file and submit that file to the endpoint, to the essentially using the main.py file. So in this case, we're saying render that file or render that template from the HTML file. Here's our Flask route to upload it. It's going to do a get and a post command. In this case, we're posting the file itself that came from the upload. It's going to send that as a request. Here's where we're defining our storage account key for the location of the image that we're going to save. So it's going to be in our cap images data lake. Here's the URL for that. Here you can remember in the Jupyter notebook, very similar, right? We're creating a new blob or a new object where it's going to have that file name of the image that we're uploading. And it's going to then create and write the data into that file. So essentially, we're uploading an image to the Azure Data Lake instance. Here's where we're pointing the URL for that scoring endpoint that we're going to use, the API key that we're going to use to authenticate, the header information. Here's where we're pulling in the file name. So this is where we're kind of creating our JSON payload, right? So image key with the file name as the value. We're going to do a JSON.dumps, so we're going to encode that as a string, and that's going to be sent as our body to the API endpoint. Here where we're going to submit our request, we're going to return the response from that request. So again, this is going to be our output from our scoring file, which is 0, 1, or 2. We're going to read that response and return it as part of this, this little mini application that we wrote, right? So this is nothing fancy. Again, keep in mind this is our scoring file that we submitted when we created the endpoint. So you can see here it's going to return the image result is and some kind of number 0, 1, or 2. Okay. So if we actually open this, let's take a look at what this does. So this is my test container again in Data Lake. There's nothing in here. Right now I'm going to upload or open my upload.html. Okay, so this is just that very basic HTML file I showed you running locally on a Flask application. I'm going to pick a file here. There's a couple. So one here I just have named X-ray. Okay, so you can see it's x-ray.png. There's no label on here that tells it what type it is, if it's COVID, pneumonia, influenza, pneumonia, or healthy. We'll pick this one. And very basic submission. I'm going to hit submit on this, and it returns the result is 2. Okay, so if we refer back to our paper here, zoom out a little bit. COVID-19 pneumonia images are labeled as 2. Okay, so that means that this is a COVID-19 pneumonia lung based on its chest X-ray. Now, what this actually does in the background is it's saving this file to our blob storage into our data lake. The reason we did that is just so we can track files for inference at a later date. We ran this over another additional 1,000 images when we did our test. So not just a single upload here, we ran it through 1,000 programmatically. And essentially that return, that's where we got our result of a 0.95 F1 score. So that's kind of the process that we use for doing this. This endpoint again is a REST API endpoint. You can do it through Kubernetes or any other endpoint. You can also download the model and do it locally if you just wanted to do local inference on your machine. But that is essentially the method that we used for building a convolutional neural network to classify chest X-rays on whether they were COVID-19, influenza pneumonia, or COVID-19 pneumonia, influenza pneumonia, or otherwise healthy lungs. And that's some of the power that you can get through Azure ML. The benefit to this is everything was done in Azure ML with the exception of storage just in Data Lake. So no local compute, deployment, inference, everything was done here, and it's very straightforward and easy to use. So if you have any questions, feel free to reach out, shoot me a message on LinkedIn. I'll put some information in the description below as far as how to contact me if you have any questions. Also feel free to comment on this video. I'll plan on monitoring the comments as well. And if you have any suggestions for future videos, or if you are interested in learning more about convolutional neural networks or the actual workings of a neural network, please let me know.